The broadcast is now starting.
Good afternoon, everyone, and welcome to the Research Results webinar. My name is Mike Fitch with the Ohio LTAP Center here at ODOT, and we appreciate your participation. As we get started, please take a moment to locate the questions box in the GoToWebinar panel. During the presentation today, please use the questions box to send in any questions you might have. Please note we will discuss all of the questions at the end of the presentation. Looking at the handout section of the GoToWebinar panel, please note also that a PDF copy of the presentation is available for reference. With that, we will go ahead and turn things over to Munir. Hello.
Yes, good afternoon. Thank you, Mike. Good afternoon, everyone. My name is Munir Nazal. I'm a professor at the University of Cincinnati and a director of Center for Smart, Sustainable, and Resilient Infrastructure. Today, I will be presenting the results of a study on establishing minimum specification parameters for cold mix used in winter pothole patching. I would like first to acknowledge my co-PI in this project, Dr. Ala Abbas from the University of Akron. I would like also to thank ODOT and FHWA for sponsoring this study. Special thanks to the technical liaison, Dean and Julie, and as well as ODOT staff members in District 3 and 8 that helped in the field activities as part of this project. I'd like also to thank Ms. Jennifer Spriggs for her time and assistance during this project. This is an outline for my presentation. I will start with a background that leads to the objectives of this study and give you an overview of what we have done. This study has two phases: the laboratory testing program. So we'll start with that, then move to phase 2, which is the field testing program that we have, and then we will have conclusions and recommendations and end with questions. So as you know, that ODOT and most, I would say, transportation agencies use cold mix for patching potholes during the winter. Typically, there are two main types of cold mix. The generic cold mix, which typically is plant produced and provided in bulk, and then we have the proprietary mixes, which are typically come in bags or can be also purchased in bulk. There have been several research studies that have indicated that the performance of patches and the longevity is related to the properties of the cold mix. However, the studies really did not identify what are those properties that can be used to examine the performance of those materials and basically can be used to ensure the longevity and performance of installed patches. ODOT and I would say the majority of transportation agency, whether it is DOTs or local public agencies, currently they do not have specification, a standard specification for cold mix. And basically, they do not have a measure to ensure the quality of a cold mix, whether it is generic and plant-produced cold mix, or basically it's a proprietary and it is included into ODOT approved basically, or a list of materials. So as a result, there is a need to develop those, or there was a need to develop those specification to ensure the performance of patches. So the objectives, and I will start with the ultimate goal of this project, was really to develop those specification for cold mix specifically used for winter pothole patching to ensure satisfactory performance and the longevity of patches installed using those mix. Within to basically achieve this goal, we had really two main objectives. The first was identifying the properties that affect the performance, durability, and then also identify the threshold limits for those properties that can be used as an acceptance criteria and in the specification. So the project had multiple tasks. We started with identifying the current state of practice and identifying really the cold mix materials used by ODOT and determining, identifying within those materials, cold mix materials, the experience of the materials or ODOT with those materials. We also did a literature review as well as a survey, a national survey, to determine if there is any standard specification used for cold mix. And we did not really, at least at the time that this survey was conducted, we did not really have any standard specification for cold mix. So based on that, we developed first a laboratory testing program. I will be talking about it in a moment. That led to developing a draft specification, and that specification was then validated through a field testing program. As I said, we had two phases. In phase one, the focus was on the lab testing. So as we talk about it, we collected different materials, different cold mix materials and their components. And when I say components, it's the binding agent and the aggregate. Basically developed a mixing criteria and aging and curing a protocol to simulate what we have in the field. And then we did a comprehensive lab testing program to determine the properties that are able to detect the effects of the binding and aggregate. And also we had a previous study that we used cold mix materials, and that helped us to identify what are the limits that needs to be set based on our lab testing results. In phase two, we used different cold mix materials, both generic and proprietary, as well as bulk and in bags. And basically what we have done is we use them to install patches in different locations within Ohio, focusing on different climates. We selected sites in the Northeast as well as the South West. And based on that, we finalized our recommendation and the specification. So phase one was the laboratory testing program. And in phase one, we selected 8 different types of, or 8 different aggregates. We had 5 limestone and 3 gravel. All of those aggregate materials had been used in producing a cold mix, and that's one of the reasons why we have used them. Basically, the properties, as you can see, we try to make sure that we have a materials with different properties, specifically low and high absorption. We tried also to look at the percentage of fines or passing 200, and you can see that we have here a range that you can see. We selected 3 different binding agents. Those binding agents are used in producing cold mix in Ohio as well as outside Ohio. And basically, we conducted different tests to characterize the properties of the binding agent. And basically, one of the things that we have is looked into is conducting the dynamic basically shear test, as well as a new test that we used and adopted, which is the tackiness bonding energy test, which helps us basically in determining the adhesive properties of the binder. We did different aggregate binder combination. Basically, we had 8 aggregates and 3 binders. I would say, tried to have a full factorial, but it was we were short of basically 2 mixes, but we had an overall 22 mixes that were prepared and tested. The tests that we have, we basically looked at the properties that we thought that will impact the performance, starting with a cohesion. We know that the cohesion of the mix will affect that. So we had a torque test that was actually developed as part of another ODOT project. And basically, we also looked into stability of the material. We looked into the ideal CT as well as the Hamburg loaded wheel. The stability, it's telling us more about strength properties as well as ductility. So both are within that. And then we have the moisture susceptibility as well as the stripping potential there. And we use the boiling test for that. We also looked into workability, and we evaluated different tests, and the test that we found to be seen or that related to the observed workability was really looking at the curve, the tilting moment curve coming from the super pave gyratory. So basically compacting a super pave gyratory at low temperature and basically looking at the area under the tilting moment displacement curve, which is basically shown here. This is what that area, we are calling it the shear stress curve index. The testing program results. So this is showing the different aggregates and the binder. We have seen that the ITS, which is the indirect tensile strength, this is a parameter that is coming from the ideal CT test. It's typically is an indication of the strength of the materials. For this particularly, because we're looking at the I would say the intermediate low temperature. This is important. And as we will talk about it in a moment, it can be also related to basically the rutting potential of the coal mix. So this ITS, the higher the number, the better the strength, and the higher the strength. As you can see, we can see that the second binder type in general basically resulted in the a higher tensile strength as compared to that. And again, this is when we are comparing for the same aggregate, the highest basically strength was when we use the binder type, followed by, I would say, the third binder that we have used. The parameter that the other parameter that we looked into was the CTI, which is the cracking tolerance index. It's a parameter that is currently being used to evaluate hot mix asphalt, and it tells us about the cracking potential. I would say the ductility to a certain degree of your material and its tolerance to cracking. Now, one of the things that we have been looking into in the results, again, the second binder seems to be basically having a better CTI, and basically we looked at for this particular data, we looked at mixes that have been used in the field in a previous study, and what we looked into, what was the acceptable or materials that had good performance in the field based on the previous study, and then we looked at what the number was here, and basically we found that basically a CTI of around 60 was really the parameter that we have. One important thing that I would say, that again, this was later on verified, but one of the things there is that the CTI seems to be affected by both the aggregate, and it's also taking in consideration the binder. So it is a parameter that was able to differentiate between basically, or to detect the effects of changing the binder type. The other parameter or test that we had is the boiling test, and the main is the percentage of material showing stripping. This test is I would say it's a very easy test, but the thing about it is that we found also that the stripping parameter seems to be also able to distinguish the effect of the binder and the aggregate on the performance. So one of the things that you can see here is the second binder or binding agent there had a lower stripping, which means it has better resistance to stripping and to moisture damage. So it has better basically durability as compared. So the binding agent seems to be one of the main factors, but again, as you can see as well, the aggregate gradation as well as type will play a role. Again, based on field data, what we observed is anything that is less than 10%, which also is the according to the standard, basically for this test, which is the boiling test, the 10% is the maximum allowed stripping. So we use it based on the field as well, based on that number. And again, you can see here that anything below the 10% is acceptable or have acceptable performance. The cohesion was tested based on the torque, and that torque test basically enabled us to look at how the effect of the binder as well as the aggregate. Again, second and third binder seems to have a better cohesion as compared to the first binder. But again, also that depended on the aggregate, as you can see. Based on the data that we have for certain mixes that had good performance as well as those that did not, we have set 120 torque pounds per inch basically as the minimum. So anything above that basically would be. Now we change that later on, but this is basically based on the lab testing. The other important thing was the rutting, which is correlated really with the dishing. Dishing is basically can be a big problem for potholes. So you can have a material that have a good cohesion, good durability, but then it does not have the enough strength basically, and as a result, it will you will have a dishing in the patch. So based on what we have seen is we looked at materials that have shown based on field that have shown basically high dishing, and we tried to look at the parameters. So what is the minimum number of wheel passes that will enable us to ensure that we will not have a dishing? The number was around basically 2,500. One thing that we noticed is that the Hamburg loaded wheel is a test that might not be readily available at the current time with a lot of contractors as compared, for example, to the IDLCT. So therefore, what we have done is looked at the correlation. And again, this is the ITS done at room temperature, and the Hamburg loaded wheel in this study was conducted at room temperature because we are testing cold mix materials. So if we found a very good correlation, and from there, we basically found that basically the 2,500, the equivalent to that is a ITS of 45 kPa, and basically this is what we have selected as the minimum criteria to ensure that dishing will not happen. The workability was, we looked at basically the material and how workable the material is, and basically by that we tried to see, there was one material that was hard to compact, and had based on observation also it was hard to work with, and basically based on what we found, it's any material that have that shear index of lower than 7.5, then basically it should have acceptable workability, and it should be workable in the field. Also lab testing, as I will be talking about in a moment. So we did 230 patches. We did those in the installation of the pothole patches, were in different sites in north, east, and southwest Ohio. The patching itself was done by ODOT, Lorain and Hamilton County in both in District 3 and District 8, respectively. And you can see that we have used a 12 materials, those 12 different materials, as you can see there. Basically, we looked into having a proprietary material and as well as a generic, both bagged and a bulk. We tried to have a minimum of basically at least 5 patches, but in the majority had at least 10 patches so that we are able to have conclusive results. Again, most of the work, because it was on an interstate, we basically had to do it during the night. We used basically a system that was developed to take initial pictures and location of each patch, and each patch was labeled. And basically, this is based on that system, which again, that system enabled us to take pictures while at a high resolution pictures and at high frequency while driving at a highway speeds, and it enabled us to take images of the patches that are georeferenced, so we'll be able to get the exact location. Again, we had a high accuracy GPS in there. And again, this is a picture of the system that is mounted on the pickup truck. Those are images that are taken basically before and after. What we have done is we took images directly after installation, and then we took basically did an evaluation, which is basically taking images of those patches the first week, the first month, second month, and then we took it every 2 months for up to 1 year. One of the things that we have done is we collected samples of the materials that had been used in the patching. We obtained those materials and we tested them, but we also, for one of the materials, we looked at the material properties with time, and basically that was by sampling the material after 4 months and 8 months, and basically that material was also tested. The main test that we conducted are performance related, which is the ideal CT torque as well as the boiling test. Here I'm showing the ITS, and basically one thing that we have seen is that in general the materials that was used in this study, basically all those materials actually had that acceptable criteria, and basically they had more than 45 ITS. Some materials had a very high strength, and again, that very high strength might not necessarily indicate that it's better performing. It means it is a stiffer material, which means that it can resist dishing more. Now, within the CTI, again, we had materials that did not perform, but one of the materials that performed poorly, and we will see it later on, is that M12, which is an aged material. Basically, that aged material seems to have again failed, and again it is not meeting that criteria of the 60 that we have. The stripping is one of those parameters that was really good indicator of the performance. Again, that material that failed, and again, like the focus on that material, because the other materials actually performed generally well, at least within the evaluation period. But the M12 actually failed within a month of basically of installation, and it had very high stripping potential, which again indicate that basically stripping is a parameter there. Now, one of the things that we looked into is how the different properties change with time, and the property that we have seen that is changing significantly is the percent stripping. And the this material was good initially, less than 10, but then after 4 months, basically it was more than 20, and then after 8 months, it was more than 40. And again, we had actually done the 12 months, and the 12 months was actually is still above that 40%. So one of the things that we looked into was to look into the data that we have collected in the field, is to determine the survivor life, mainly because a lot of the batches did not really fail, or some did not fail, and there basically we needed to do a survivor life to analysis to determine the survivor life based on that analysis. We did also the Cox proportional hazard model. The hazard ratio that I will be showing, it tells us the higher it is, or the higher it is as compared to 1, this means that basically there is a more potential for failure. And again, we had also the likelihood ratio test. So in here, there are, from those results, and again, we have a lot of the results there, but one of the things that I would say that from the hazard ratio, and again, just to remind you, if we have a hazard ratio above 1, this means that parameter will or material is indicating that it's affecting it adversely, or it will cause the patch to fail. So using that M12 aged material, basically it seems it's a had the highest, and basically its effect is significant at 95 confidence level. Also, there is another material, which is the M3 used in the Northeast. The other important thing is just using a material in Northeast as compared to Southwest. That, and again, the main difference, because the locations there were had similar traffic, the main difference is really the weather condition. I would say the most important thing is number of freezing days. This is the one that, as you can see here, having the same material, but in different location will lead basically to it will lead basically, if we're having it in the Southwest, it will lead to a lower probability of failure there. That is general for all materials, but we have found that certain materials, as we will see, is more prone to the weather conditions as compared to the others. This is the survival life. And one of the things that we have seen again, the probability, this is the probability of survival. So basically, if you want to do the probability of failure, you need just to subtract. So we had a material, which is the M11, M12. The M11, both of those materials were produced at the same plant. And basically, the difference is one has been used 1 year after it was produced. So it's an aged material. So it was produced, used in the field, and then this, there were some leftovers, so it was used in the second season. And what we found out basically from the survivor life, its probability of survival is low, indicating that within a month or so, it will fail, which might cause, and again, the average mean for that was actually less than a month. One of the things that we looked into is looking at the same materials but at different locations. And again, what we observed is some materials, as you can see, for example, the M2, it performed really well in the southwest, and again within that weather, but in the northeast, the probability of survival was decreased because of that. And again, applied to that the M7, the M0, which again, like the designation of the materials, those are again different cold mix materials designated there because we needed to not provide information about the producer. What we have there is some materials like the M0, we did not really see a significant difference in terms of the survival between the southwest and the north east as compared to the other two materials. Again, within the northeast, we have seen some materials, including the M12, and again, the M3 specifically had basically failed, and there was a lower probability of survival as compared to the others. But in general, the cold mix that were used in, at least in the field study, in general, performed relatively well. Basically, in general, and again, the patches, I would say, that were installed performed well. The southwest, in general, those materials that we have used, and you can see here, they had good survival or much better survival rate. In most of them, again, the survival rate within the period of evaluation was really more than 90% survival rate. So we did a cost analysis, and in that cost analysis, the focus really was on materials that are basically meeting the specification. We tried to use a material meeting the specification with an average cost, and then we had also material that is much more expensive than the other materials. Still, of course, it's meeting the specification, but it's more expensive. And then we had the material that the same as the first material, but it does not, in terms of cost, but it does not really meet the specification. We did different analysis, the 6 and 12 and 18 months. And one of the most important things that we have found is that the cost of materials that is failing and is not meeting the specification would basically, using that material will lead to almost more than doubling the a cause for audit. The main reason for that if a cold mix is not meeting the specification, is not performing well, and it's failing basically prematurely within a month or two, then that will cause basically the repatching. And looking at the data, really the most expensive part of the patching is really the labor rather than material itself, which means that even with using the most expensive material, if we go to a 12-month span, we found out that basically the material that has much lower initial cost but is not meeting the specification will be actually will lead to more to higher cost for audit to patch those materials. So basically those materials basically should be avoided, because the cost, they can increase the cost of patching significantly. So the conclusions, we have seen that basically using aggregates with low absorption was basically lead to a less susceptible material to moisture damage as compared to the ones with higher absorption. So they will lead to more durable material. One important thing is that the CTI and the ITS coming from the ideal CT, both are influenced by the binder and the cold mix. The CTI seems to be indicate to detect basically differences between the binders, and the ITS seems to be a good indicator of the dishing potential, and can be used to evaluate basically the cold mix in terms of the dishing. The boiling test was used, and it seems the stripping percent coming from the boiling test seems to be a good indicator of durability and performance, and that was based on the lab testing as well as verified in the field. One of the things that we have seen, that some materials seems to be more resilient to the weather condition, and then we have more materials that are more prone to the weather conditions, and that means that that the same material might perform differently within different regions of Ohio. The other important thing is the stripping potential, and basically the results is showing that the material properties and durability will change with time, and I'm talking about here bulk cold mix material stored in a stockpile. Basically, therefore, that the material properties needs to be checked with time. The cost analysis indicated basically that materials not meeting the specification can increase the cost of patching for audit, and basically it will it can be more lead to higher cost as compared to a more or much more expensive material. The main recommendation, this is basically our recommended specification. We have different tests. I would say that that one of the most important thing is that each of those tests is really capturing part of the performance, and therefore we had to put multiple properties, so you can have a material that has very high ITS value, and we have seen it, but a low CTI and ideal CT, which means that it will fail. So that combined, I would say the first 4 parameters are important, are good indicators of the performance in the field, and specifically the boiling test, it can indicate basically the performance as well as the durability of the material. We are also recommending that if a cold mix is stored more than 4 months, and basically it's stored maybe more than one season, basically it needs to be tested after the 4 months using the boiling test. And basically we're recommending that if it is less than basically or more than 20% stripping, then basically that material should not be used in the field, because the patches installed using that material will or may prematurely fail. So thank you for attending this presentation, and if you have any questions, please let me know.
All right. Thanks, Munir. And as a reminder to our audience, the questions box is open. We do have plenty of time available for questions, so please feel free to type those in. And I want to mention that Jennifer from ODOT's research section is online also. So Jen, if you have any additional information to share about this project, feel free to do so.
Thanks, Mike, and thanks, Munir, for that presentation. It was a wonderful presentation, and I think this is a great project that we got a lot of information out of. We do post these on our website under results presentations. So if you're interested in looking at any different research that we've done and we have results presentations or final reports, you can find that on our website.
Very good. Thanks, Jennifer. Okay, well, we have a few comments already. First of all, thanks and great work. So that's a very nice comment. Okay. Question from Georgianne. In Dayton, Ohio, hot patch is available year-round for $5 more. Is this better in the long run?
Although we did not test in this specific study a hot mix, we have done a study for OREL and ODOT. I think the results there have indicated that basically the hot mix, when it comes to the hot mix, one important thing is the compaction. Cold mix is or performance of cold mix is less affected by the compaction as compared with hot mix. What we found, again, not in this study, but in another study, is that the hot mix, if it is not compacted well, then basically it will perform poorly, and therefore, in taking in consideration everything, not only material cost, but also taking the productivity, how many patches you can install with a hot mix if you have to compact it well as compared to cold mix. So cold mix might be a better option, specifically for smaller potholes or small to medium size, but when it gets to be larger, then where you have really to compact, then basically the hot mix will be better. So, but this specific study was focused on cold mix, and we were trying to develop basically the specification there, and therefore basically the cold mix, if the problem typically with the cold mix as compared to the hot mix is that the quality of the hot mix is typically more controlled, but with this specification, I think that the cold mix will be basically can be controlled as well. So.
All right, thanks, Munir. We have a question from Brian who says, can we get a list of the 12 material brands used in the research?
Well, that's, I think, a question to ODOT. I think that I cannot really answer that. So I think refer that to maybe ODOT research section and maybe technical liaison, because, yeah.
So I will say that at any time, if they choose to release that, they can. However, at this time for this specific report, we decided not to do that because we didn't want this to be focused on calling anybody out for not making a good mix or saying that someone's mix was better than another mix, or having a situation where maybe in a couple years or a year there is a better mix. And now we've said that one particular mix is the best, but there's another one on the market that didn't get a fair comparison. So this report was based on just taking the results and trying to come up with a specification that would allow us to get the best results. So whatever businesses are willing to put in and meet those specifications are the ones that are going to be successful with the cold patches. So I would say if this is something that you're trying to do in your area, taking the specifications.
Yeah. And again, I think Jen have mentioned and very important. You have the specification because we cannot really guarantee, and that's something that we have seen. We cannot really guarantee the quality of the mix. So that mix coming from a certain plant or certain vendor, maybe during the study was performing well or poorly, but the vendor changed something that we do not really know. So it might be not really performing as it performed during the study. And the better way of doing it is really the specification. So any material, doesn't matter who's the vendor, who's the producer. If it meets the specification, then it can be used. If it does not, it does not matter who's that vendor, and that's maybe one of the reasons why we had so. Yeah.
All right, thank you. I copied into the chat, Munir. Yeah. There's also a question from Eric with some detail there. About the potholes patched in the field.
Yeah. We used a like all patches that we were evaluated, just to we used the same method, and so we followed the same protocol so that we can compare all materials in the same way. We used basically I would say a tamper to compact, and we even determine, like, just to make sure that we have a fair evaluation, we use the same number of tamps or blows, I would say, per square foot, so that we can have the same compaction effort. We did not really focus a lot on the impact of in this study, at least, the effect of basically the procedure followed for a compaction and installation of the patch. But I would highly recommend, there is another study that we have completed about a year ago, year or year and a half, for Ohio Research Initiative for Locals. And we compared the different installation and compaction method. And I think I would defer Eric to that study. And if he, I think I can send him a link if he contact me directly by email.
Thanks, Munir. In the chat box, there's a question 4 from Nicholas.
That's the hot box. Again, I think that one of the things that in all materials we had made sure that the material should be at least 4 hours prior to installation. It's at least at room temperature. I would say that between 70 and 80 Fahrenheit, if it is in a hot box, to be within that range. Again, we did not really study it in this particular project, but this is basically what you have. If it is, if we have too cold or a cold mix that is frozen, or that have low temperature, then it might not be easily, it will not be workable, and it will be hard to place and compact if it is compacted, and basically as a result it might not perform well. So the preference it is that it should be within like that, I would say room temperature between the 70 and 80 Fahrenheit. If it is in a hot box, then 80 Fahrenheit would be recommended.
Thanks, Munir. Question from Don. He says, was there any cold mix sample used made with emulsion based?
I would say because a lot of that binding agent, I think what we know is it is made by cutback, but again, some of that information is proprietary, so we do not really know. Some, I think, one of them, and I'm not sure, is not a cutback, but it is not a regular emulsion. It is basically it's an improved binding agent. Again, I don't want to go into details about that, but I think that the majority of cold mix evaluated had a cutback. Yeah.
All right. Thanks. We do not see additional questions at this time. There are several comments saying thank you for the study. Much appreciated. So if there are additional questions, please feel free to email those to Munir or the ODOT research section. And I'll mention also that within the next day or so, we will send out a follow-up email to the webinar attendees with a link to the recorded video from this webinar and a link to the PDF presentation. So thanks everyone for your participation. We appreciate it, and have a great day.
Thank you.